Hello everyone. I'm Wei Ping, and today I'm going to talk about the characterizations of mechanical properties of particles. Before we start the actual lecture, let's do some self-assessment. Let us see how well do you know about this topic. So I'll give you about 5 minutes to attempt the question. Right. Okay, so if you're finished now, then let's proceed to the actual lecture itself. So, what are mechanical properties? So, let's have look at some real life example so that you can better relate. So, I'm not sure if you have ever been so stressed that you feel that you need to grab onto something. So, if you look at then the stress ball. The interesting thing with stress ball is that, if you squeeze it, no matter how you squeeze it, it always goes back to its original shape. And the question is, why is that? So similarly, if you now have, let's say, a flour dough or a cookie dough of the same size, and you squeeze it, then what happens? Will it go back to the original shape? Probably not. It's going to, stay in that shape. And why is that? So another example is, do you like drinking? Using a very elegant, glass flute. And I'm not sure, if you ever, actually drop it accidentally. And what happens, if you actually drop it? It basically, will shatter into pieces. And now, if you change it to, say, a plastic flute instead, and you drop it, it wouldn't break. And why is that? So another example, let's look at then, let's say, a metal sheet. You can, essentially, like bend it and then actually also shape it into any shape. And then it wouldn't bounce back, and it would stay in that shape. So it's, that's actually very shapeable. So why is that? And an example of this, I wouldn't recommend you try it. If you have an iPhone, actually, like there were some like reported incidents. You can actually bend it, and you can see like some example here. Like this guy was trying to bend the iPhone, and then you can actually bend it. And last but not least, cheese sticks. Like if you like some very nice cheese sticks, like you can actually stretch it, and then you can actually also return it to the shape. It's actually very stretchy. And why is that? So basically, like all of these, like behaviors of materials, like is actually, like manifestations of the mechanical properties. So essentially, the mechanical properties of a material will decide, like how materials will perform and behave when they are being exposed to external forces. Okay. So the scope of my talk today, but particularly, like we're going to talk about the mechanical properties in the context of particle breakage. So particle breakage, like can be, like desirable or undesirable, and like particle breakage actually happens, across, different industry. So desirable, breakage, we're talking about something like milling. Like we want to mill something into smaller particles. Like for example, with flour, you want to, grind the grains, like small enough so that like you can, use it as a flour. But we also, would also come across with some unwanted particle breakage. Like basically, for example, I have a case here, of our FCC and moving bed reactors, where you have, like the catalyst carrier bit, and then, like through the cycles of, the reactions inside this reactor, then eventually, the carrier bits, like they get worn out, and then eventually it can actually lead to fragmentation. So this is something that we don't want to, because like it could actually cost a lot of money, as a result of the breakage of the carrier bits. So then the next question is then, can we somehow like do some like simple characterizations, and then like with the characterization that we do, can we then like predict like the breakage propensity? Can we somehow predict how a material will behave like under like externals and like influences and external forces? So the first part of my presentation today is going to be circling around like high school physics, like talking about like brittle materials, ductile materials, and of course like we also talk about something that's in between, something that we call semi-brittle like materials, where they undergo semi-brittle failure. And following that, like I'll talk about like the characterizations of some of the like more common like mechanical properties that we use in describing particle or like material failure. Right. Okay. So mechanical breakage. So what affects mechanical breakage? Like what affects like particles or like objects and how they break. So if you have an object, and then how are we going to break it? So how is it going to break? So it's actually affected by the mode of loading and also the material properties. By mode of loading, we are talking about like how you actually load, or how you actually stress, like the object. So be it by impact, you shear it, you compress it, you crush it. So these are all like different types of like loading you can do to an object. And apart from like how you load it, and then like the rate that you load it also plays an important role. Like so if you load it at a much faster rate, then the materials like will behave differently, and then they will break like to a different extent. So the three major types of failure modes we have, as I mentioned earlier, we have brittle failure, semi-brittle failure, and ductile failure. With brittle failure, like it is actually caused by the ruptures of the bonds, like between like molecules. Whereas for semi-brittle failures, like it started off with dislocation mobility. Basically, like the molecules or atoms, the particles, they get dislocated. But then, when the stress, is high enough, or the force applies high enough, then the bond starts to rupture, and that's how they fail. For ductile materials, it's mainly caused by dislocation mobility. Ductile material, as you all know, is actually it's very malleable. you can, you know, like apply, you know, a large amount of force, and then it just keep on, you know, like deforming and deforming and deforming. So, you know, this is caused by mainly by dislocation mobility. All right, so brittle failure mode. So some of the examples of material which undergo brittle failure, classic examples would be glass, like the example that I showed earlier. You know, like if you have a glass, when you drop it, then, you know, like it shatters, you know, like almost instantaneously. So it is actually caused by internal flaws of materials, surface flaws of materials, and associated deformations. And a typical, you know, like characteristics of brittle failure is that, you know, like you don't see plastic deformations. So basically, you know, like what I'm trying to say is that, you know, like you don't observe, you know, like the material, you know, like getting deformed before, you know, like they actually, you know, like fractures. So, but there's actually, you know, like they do undergo some sort of, you know, like plastic deformation, but it is so small that, you know, like you can't actually see it. And what happens is that, you know, like as soon as, you know, like cracks start to propagate, you know, like very quickly, and then, you know, like it starts, you know, like breaking up into, you know, like a lot of like pieces. So one example here you can see here is that, for example, if you have a sphere or, you know, like a metal ball, then, you know, when you stretch it high enough, then, you know, it breaks into, you know, like this orange segment, which is, you know, like a typical, you know, like failure, you know, like of you know, brittle materials. So materials, you know, which undergoes brittle failure, you know, they can fragment. Let's say, you know, they can fragment into big pieces, and then can apart from that, they can also chip and wear, as shown here. You can see that, you know, like if you apply some sort of shear deformation, then, you know, like the surface, you know, get worn off, and then, you know, like also in some cases, you know, like some chips may actually come off from the surface of the material. So, quick summary of brittle failure mode. So, pre-existing internal and surface flaw affects the strength of the material. And for high compliance materials, it's actually caused by surface flaw, whereas for low compliance material, it's actually caused by internal flaws of the material itself. And the stress field is independent of the strain rate. And to predict the breakage of brittle materials is actually quite difficult. And mostly, you know, like people will do, you know, like will actually use some sort of statistical analysis to, you know, like to basically describe brittle failure. And the most famous one would be, you know, like by using whiteboard analysis to describe the data. And again, then this is an example which I showed earlier, which is the carrier based using the FCC reactor. You know, it's a typical example, you know, like of material which undergoes brittle failure. You can see that, you know, like they basically break into you know, like big fragments. And then here's another examples of porous alumina beads. Here you can see, you know, like at this corner here, we have this, you know, very classical like conchoidal fractures. You can see this, you know, very smooth curving features, which is again another, you know, typical characteristics of brittle material. Right, now let's move on to semi-brittle failure. So what's different from, semi-brittle failure is different from brittle material. I mean, the most obvious characteristics of semi-brittle material is that, you know, like you can actually observe, you know, like plastic deformations of, you know, the materials before, you know, they actually fail. So here you can say that well, the crack propagation is actually preceded by plastic fault. So some sort of you experience some sort of plastic fault before, you know, like a crack is initiated. So there are three major crack system, you know, like as you can see here. So we have a radial, median, and lateral crack. So radial crack, basically, you can, from the top view, at the site of impact, can see that, you know, the crack actually propagates radially from the site of impact. And then look at the side view. This is how, you know, like they look, you know, like how it actually propagates, you know, like beneath the surface. And also looking at a median crack, then basically, you know, like goes like all the way, or even like beneath, you know, like the site of impact. And then, you know, like from the top view, you can see, you know, a straight line like this. And the third type of crack system is called the lateral cracks. Basically, you know, like this type of crack, you know, like the surface, you know, which is parallel to the free surface of the material, you know, like they get, you know, like chip off, you know, like, and then they come off from the surface. And from the top, you know, like it's going to look something like this. Basically, you know, like a thin layers of, you know, like material that will actually come off from the surface. So radial and median cracks, they are responsible for fragmentation because, you know, the cracks, you know, like goes deep into, you know, like the sample and then cause the material to fragment. whereas for laterals, you know, like it's responsible for chipping and wear of the material. So, quick summary for semi-brittle failure mode. So cracks are initiated by plastic flow, and lateral cracks are responsible for chipping and wear. Ray down and median cracks, they are responsible for fragmentation. And indentation fracture analysis can actually be used to describe the breakage. And there are actually a lot of predictive models available in the literature in which we can use to describe this type of failure. And for semi-brittle failure, strain rate and temperature are influential. So these are the examples of material which undergoes semi-brittle failure. Okay, you can see that here at the impact side, you can see very obvious, at this side, the materials get flattened, so you can see some sort of plastic deformation. But we also see different crack system here. For example, here, you can have some sort of medium crack or rayed-out crack here, rayed-out crack, and then you can see here we also have some sort of sublateral surface crack. And then here's another example, which show the chipping of the corner of a material here, of a particle here. Right, then let's move on to ductile failure mode. So pretty sure you are familiar with ductile material. Classical examples are most metals, they are ductiles. So you can easily shape them, you can pull them into different shape. And so the characteristics of ductile failure is that they can undergo extensive plastic deformation. And crack propagation is actually very slow, and that's because they can actually absorb a lot of energy before crack can propagate. And then here's a typical example, showing the necking of a metal rod. If you pull it, with enough force, then this necking will start to form. And then on the right, these are some typical examples to show you impact, failure of these ductile materials and how they will behave under different stress. And the important factors which affect ductile failures, they are the attack angle, the ratios of the Young modulus and hardness, and also the ratios of hardness values of two surfaces, and also the ratios of the shear stress and the shear use stress. Okay, so now just quick overview of the three types of the failure mode. So then move on to some of the material properties, which basically that accounts for failures. So so the first one, so we look at Young modulus. So what's the definitions of Young modulus? So Young modulus is actually defined as a resistance against elastic deformation, whereas for use stress and hardness, they are actually a measure of the resistance of a material against plastic deformation. And then last but not least, fracture toughness. It is actually a resistance against crack propagation. So these material properties or mechanical properties, they are important because they actually account for how the materials would fail. So how do we measure hardness, and what is hardness? So hardness, like I mentioned before, is actually that the resistive pressure when a permanent impression is made, and this is typically after 8% of strain. And indentation hardness is probably one of the most common methods used to describe or to measure the resistance to plastic deformations. Some of the most common indenters are Vickers indenters, Brenner, Rockwell, Knuth indenters. And then for hardness measurement, it's actually related to use stress, work hardening, anisotropy, and geometry. So use stress. So when an indentation, when we do indentation, when an indentation is made, when an indentation is made, then actually plastic deformations is actually confined. So and therefore hardness is actually much larger than use stress itself. So the relationship between use stress and hardness can actually be governed by this a simple equation here. Hardness is simply the functions of the use stress times the constraint factor. And this constraint factor is actually affected by material properties, the indented geometry, and also the frictions. And some of the relevant properties are the elastic modulus, work hardening, and then anisotropy. So these are the constraint factors of some of the common materials. For glasses and polymers, we are talking about constraint factors of less than 3. And then for a wide range of metals, it's more or less around, like 3. And then for ionic single crystal, we are talking about, constraint factors of higher than 3. Right. So I mentioned that, to measure hardness, it's normally done by indentation. But the previous method of the previous for indenters that I was talking about, they are mainly for bigger sample. So in powder characterizations, we're interested in looking at the mechanical properties of a single particles. Sometimes we're talking about maybe 100 microns, or in some cases even less than that. With the types of indenters that I shown earlier, they're actually quite difficult, and then it can prove actually quite difficult to prepare the sample and also to indent it, because the indenters are bigger compared to the particle size. So since late 80s, then we have this new development by Pollock. So by basically this new indentation method that we call nano indentation. So essentially what's different compared to the previous indentation tests is that we can use much smaller particles, and then for this type of setup we also have higher resolution, meaning that we can do a smaller indentation, but then we get enough resolution to look at how the force and the change in depth of the indenter during the penetration or the indentation. So we have here is an example of the setup of a nano indenter. So how we apply a force is by electromagnet. Essentially, you apply current through this electromagnet, and then this coil here will get pulled towards this electromagnet. And then at the middle here we have a pivot, and as a result of this pulling force towards the electromagnet, then the indenter here get indented, basically started pushing towards the surface of your specimen. And to measure then the depth, then we have transducer here, and then the change of this distance between this plate will result in a change of the capacitance, and by measuring the capacitance, then we can measure we can correlate how much distance or how much depth has the indenter penetrate through the surface of the material. So this is an example or of an impression made by Berkovich indenter. So Berkovich indenter has this typical pyramidal shape, and it's because of this three-sided geometry, it makes it very easy to be machined to a very high precision and very sharp angle. Hence why it is highly preferred in the work of nano indentation. So here just a plot show you a typical depth load profiles when an indentation is made. So essentially what we're seeing here is the resistance of a material to penetration load, and then as a function of the depth. So we use this to infer an effective hardness. So essentially when you first start when the indenter first start coming into contact with the surface of material, then you can see that then the load start increasing up to a maximum point that you are specified, and then it will start unloading. But then it won't unload back to the original line, so there's some sort of hysteresis here, and that's due to the plastic deformation. And what we see here, around this point, this here, oops. Okay, technical issues. Free this. Okay, come back. Okay, so basically what happens is that here we get the plastic strain, and then it doesn't like the laser point. Okay. Anyway, so the maximum point here is where we measure the hardness of a material. So essentially, the maximum load that is experienced, and then you can use this correlation here. Okay, I'll stop using the laser pointers. So basically, the correlation here. The correlation here can easily use that to characterize or to measure the hardness of the material, and that is simply by dividing the maximum force by the area or the indentation area, and then the indentation area is given by this correlation here, where K is the indenter shape factor, and then HC max is the maximum penetration depth. And then the stiffness or the Young modulus of the material can be measured, by taking the slope of this, unloading line here. The very initial part here, they behave, linearly, and then the slope of that, corresponds to the Young modulus of the stiffness of the material. So, with doing indentation, we can also, use it to actually characterize crack or, the fracture toughness of material. As an example, here you can see that over here we have, again another impression made by a Rabakovic indenter, and from the side you can see that, the crack actually propagated as a result of that indentation. So, we can use this crack length here, to somehow find a correlation, between, the critical size. The critical size here, refers to the critical size that material, can undergo before, a complete failure. So Putik actually come up with this correlation here and say that, the critical size is actually a function of the Young modulus, the fracture surface energy, and also the yield stress. And then here's just an example to show you then, the propagation of the crack. You can easily measure this. And then here is a schematic showing, when you have a Rabakovic indenter, you indent it on the surface, then you can see how the crack propagates. And then by using, this, measurement, the crack length here, we can then easily then calculate, the fracture toughness of a particle given by this equation here. So essentially, fracture toughness Kc is the functions of the impression size, the crack length, the Young modulus, hardness, load, and then the C star, which is the crack size, which is A plus L, as you can see from the previous slide, A plus L, which is this length we're using. Okay, so if you now plot, the crack length, versus the load, and then this is the work done by Arteaga et al. In 1997, in a logarithmic, scale, we can see that we can get a very nice, linear relationship, and then, the slope of this line actually gives us a measure of the fracture toughness of the material. So if you now plot, the fracture toughness measure against the load, you can see that, here we have two different materials. We have lactose, paracetamol. Lactose, has a much higher, fracture toughness compared to paracetamol. And another interesting thing here to note is also that load has very little effect on fracture toughness. As you can see, that if you increase the load, the fracture toughness remain almost constant. So concluding remark for the first part of my presentation today, relationship between hardness and yield stress require considerations of the effect of material properties, indenting geometry, friction, and etc. Hardness and elastic modulus can be both determined from a single penetration test. Indentation fracture mechanics shows that the important factors affecting material failures are hardness, Young modulus, and fracture toughness. And for particulate solids, suitable techniques for characterizations of hardness, Young modulus, and fracture toughness is by nano-indentation method. And development of an understanding of tableting, comminutions, and compaction processes, they require characterizations of these properties. Right, so the next part of my presentation today is going to be looking at the characterizations of bulk deformations and breakage of particles. So breakage characterization. Okay, so I'm going to talk about the analysis of breakage mode, mainly focused on semi-brittle mode, and then of course I will also then briefly describe the analysis of breakage for brittle mode, and also looking at then the bulk behavior of a particular system. So we can do for to characterize particle breakage, we can do single particle testing as well as bulk testing. So here are some examples of single particle testing that can be done. For example, impact test, Brazilian test, Wear indentation test. And the features of single particle testing is that they are fundamental, and they actually reflect the material properties of single particles. But the problem with single particle test is that it's actually very difficult to relate it to industrial application. And therefore, in industry, most people will prefer using a bulk test. For example, looking at then compressions of a bed of particle. Looking at, for example, so here are some examples of different bulk tests: shear, fluid bed, wall milling, tumbling, and vibrations. And the features of these tests is that, of bulk tests, is that they do reflect particle interaction, because we're talking about a bulk particles where the particle gets to interact against each other, and they are closer to industrial cases. But the problem with bulk tests, that they are sometimes they are quite difficult to interpret, and they're useful for relative comparison. But if you're not careful, then you can actually give very misleading interpretations of the data that you get. So for brittle filament, so I'm going to talk about the analysis of, as I mentioned earlier, brittle materials. The breakage of brittle materials is actually very difficult to predict, and then most people actually use Weibull analysis to describe it. So here is an example just to show you Weibull analysis, which is the probability of fracture S is the functions of the stress you apply to the material, and also the crushing strength of the material. We have the M and Z as the fitting constant of this model. And we also have a model by Vogel and Poikat, in which basically it's Weibull distributions, Weibull analysis, but instead of the previous formulation, they actually try to then incorporate the properties of material by introducing Fmet, Wk, and Kmet, which they refer to the material particle size, the kinetic energy, and also the minimum kinetic energy, which causes particles to break. Right. So move on to semi-brittle failures. So here I want to then describe a model for chipping. So here we have the models of Guthrie and Jones, and we can see here an example to show particles undergo chipping, where the corner of the materials get chipped off. And so it's governed by this equation here, where R star is the fractional mass loss, and it is a function of the density of the materials, V, which is the impact velocity of the impact, the D, particle size, H, hardness, and Kc, the fracture toughness. And A here is a proportionality constant for us to fit the data. So here, just to show you some examples of different, so we have here magnesium oxide, sodium chloride, and potassium chloride, this nicely lab-grown, big crystals, big cube crystals of these materials, and then how they undergo chipping as a result of impact. You can see the side of the corner chip off, and then coming back to the failure mode of semi-brittle failure. So we have this sublateral crack, where a layer of the material get broken off from the material itself, and then you can easily calculate then what's the volume of this this chip, and fit it into the equation. So here, if you plot then the extent of breakage R star, as I mentioned earlier, is the fractional mass loss of the material, and then against the impact velocities, you can get this plot here. So here, four different series, they are representing different particle sizes. So the red line here represents the smallest sieve cut of 250 to 300 microns, and then the purple lines here represents the 425 to 500 micron particles. And this type of analysis, they are done by gravimetric basis. Essentially, what I mean is that we do that by sieving, something that Professor Tatsumi Matsuyama mentioned yesterday test. So we do sieving, and then these sizes here are the standard sieve cuts that we use. So we separate the particles into different sieve cuts. We subject them to different impact velocity. We look at the extent of breakage. This is what we get. And then the conclusion we can see here, what this plot is telling us that bigger particles, they have a higher tendency to break compared to smaller particles. So you can see here different size range, and then here is just some of the parameters that we get as a result of this type of analysis. So you can see that breakage propensity, they increase with size and impact velocity, as I mentioned, and then C1 over L, which is like this, and this basically this group here, it remains relatively constant. Basically, this group represents the material properties of a material. So we can say that with this, Gadry and Young's model can nicely describe this type of failure, semi-brittle failure. So again, continuing looking at the same model, if we now plot particle breakage or fractional mass loss as a functions of the particle size and velocity square, we can get to this linear relationship. And then very interesting thing you can get here is at this x-intercept here. This is actually a very important and actually very useful parameters we can use, as it actually signifies the transition point from no breakage to breakage. So with using this, we can easily design different operations based on this, telling us that if we have this particle size, what sort of minimum impact velocity is required for this size of particles to break. Right. So that's for chipping, and then now we move on to fragmentation. So to describe fragmentation, then here again for Gadry and Young's model, we can look at then sorry, not Gadry and Young, yeah. So we can look at the force required for particles fragments. Here some snapshots of high-speed camera showing particles which undergoes fragmentation. You can see that it breaks into half as a result of impact. And then here are some transition velocities. So this different velocity describe the transition point from plastic deformation to chipping, and then from chipping to fragmentation, and also here we have a limit of breakdown. I will go through them in detail here. Right. So we talk about characterizing particle impact breakage, and then the tools that we use is something that we call the single particle impact tester here, as you can see, on the picture on the left here, which is a device here we have in LIT, which is in-house built device. So here is a schematic. Basically, how it works is that you apply a vacuum pump from the bottom, and then we feed particles from the top, and as a result of the vacuum created inside this chamber here, the particle gets sucked down, accelerated, and impact on the target, which is a very rigid target made of sapphire glass. And as a result of that impact, particle break. So towards the end of the experiments, we collect the particles, at the bottoms of this porous media here. We then characterize, basically the extent of breakage as a result of the impact. And then here, of course, we can also look at different impact angle by putting additional target here with incline angle. But the question is that with this type of equipment, it is not commercially available. So for companies who wish to use our method, or the Gadry and Young's method, to characterize particle breakage, they can't do it without the single particle impact tester. And hence why we actually then develop some method based on commercially available particle size analyzer, as you can see here, which is the Malvern Analytical Mastersizer 2000. So we have this work on this development, looking at using this the dry disperser of Malvern Mastersizer 2000. Here you can see the schematic of basically disperser of this device. It had this L band here. So what happened is that when we do particle size analysis using Malvern Mastersizer 2000, the particle get accelerated here. And then they hit on this L band here as basically it is intentional to help break down any agglomerate. But for very friable materials, we actually found that as a result of this impact, particles actually undergo breakage. So this is actually not wanted, because when you want to measure particle size, you don't want the particles to break, because if they break as a result of this dispersion, what you get towards the end is not representative of the actual particle size. But for us, this is actually a good news, because we actually want to break the particles, and then we want to have a quick way to then measure the particle size. So that's why our Malvern Mastersizer 2000 is actually a perfect tool for us, because we can use it to break particles, and then subsequently we can quickly pass these broken particles towards the laser, and then we get a size distributions of the broken particles. And but of course, to use Gadry and Young's model, we need to have an idea of the impact velocities of these particles, when they are inside the system. So unfortunately, like with the setup of Malvern Mastersizer 2000, we can't actually measure, like the impact velocity, like by using a high-speed camera or any sort. So, like the way how we can then characterize or, like predict the impact velocity is by CFD modeling. And then this work is actually done by our previous colleague, Dr. Muzammil Ali, in which, like he performed some sort of CFD simulations of this Sirocco disperser here, looking at, like having the particles of different, like density, size, and then what sort of impact velocity they will experience, like under different dispersion pressure. So having done that, we then, like can have an idea, like what sort of velocity that the particles undergo as a result of impact, and we can then, like then correlate this using again applying Gaudian-Young's model, but like slightly modifying. Instead of like looking at fractional mass loss, we now look at like the shift in the specific surface area of the material, and then plotting them against like again the density, particle size, velocity. We then get like this type of correlation. You can see that here we've got 3 different types of material: aspirin, lactose, sucrose, and then for this you can tell that like the slope of this line gives us like a measure of the breakability of the material. And looking at here, you can tell that like aspirin breaks easier compared to like sucrose and lactose. So having like done this, like we can then nicely basically apply Gaudian-Young's model even if you don't have like a single particle impact tester. So like this is the work that has been done many years ago. But then some of you may say, okay, Malvern Mastersizer 2000 is old. I mean, it's probably 20 years old now. And then in fact, Malvern Analytical, they have stopped supporting Malvern Mastersizer 2000. So to solve this problem, or to fix the problem, we also extend our analysis to Malvern Mastersizer 3000. So we perform the similar type of analysis using CFD to predict the impact velocities of the particles, like inside this disperser here, which is called the AROS. And then by performing similarly, like applying Gaudian-Young's model, we can also then use this method to predict the strength or the breakability of materials. So here we have examples of aspirin, sucrose, paracetamol, and washed lactose. And you can see very clearly lactose here has the highest breakability index, which in other words they break much easier compared to say aspirin, sucrose, or washed lactose here. And then again, the x-intercept here will give us a very good indicator on how to design a specific process. Right. So comparing the 3 different approaches using single particle impact tester, using Sirocco test, using AROS. So you can see that they actually give remarkably very close results, even though for example they are fundamentally different between impact testing and also Sirocco test. But still for example, if you look at the breakability index of aspirin to sucrose, the results that we get from the single particle impact test is 1.9, and then for Mastersizer 2000, 3000, we get remarkably good results across these 3 different methods. But then you may ask, okay, so we have laser diffractions. So laser diffractions, it's known that if you have highly acicular crystals, laser diffraction won't give you a very good measurement of the particle size. And then you may ask how do we then characterize acicular crystal? For acicular crystals, they break very differently compared to a more aqueous crystal. So, and especially in pharmaceutical industry, most of the APIs, for some reason, they like to become the elongated shape. So, how to then, we can, then characterize the breakage of this, this type of material. So we use a different approach instead. Instead of using laser diffraction, we move on to using light microscopy technique, in which we actually see the particles. So we actually look at how the particle breaks. For laser diffractions, we are using the scattering of the light, so we don't really see how the particle breaks. But with light microscopy technique, then we can do that. We can actually assess how like needle-shaped particle break. So a commercial device available for this type of analysis is Malvern Morphology G3, as you can see here. So what happened is that like we apply how it works is that we apply some sort of basically we put some materials in this well here. We apply the pulse of air from the top, and as a result of this, like particles collide against the wall of this dispersion spool, and then they break. Again, we can't really like measure the impact velocities of the particles inside this dispersion spool. Again, so hence why like with the help of my colleague again, Dr. Muzammil Ali, we performed some CFD simulations to look at the impact velocities of particles inside this dispersion spool. And having that, so here is a video to show you, like inside the dispersion spool how the particle breaks. So here, like the sample well, we put the material here, and as a result of a pulse of air, particle gets like entrained, collide against like the surface of this dispersion spool. They break and then they exit, like this this hole here, and then they settle down on a piece of glass slide for particle size analysis. So here, just to show you an example, like an evidence, like the needle-shaped particles do actually undergo particle breakage as a result of like dispersion inside Malvern Morphology G3. And this work was actually done by Sabara here, who's sitting quietly there, and then has done a nice job, and he managed to publish a paper during her MSc project. Right, okay, so here is just a case study showing like the breakage of carbamazepine dihydrate. So carbamazepine dihydrate, I'm not sure if you have experience of it, but like they are very tricky material because like they tend to be very acicular and platy. So they have high aspect ratios, but at the same time, like one of the dimensions is so small, then they're actually flaky, or platy, depending on how you want to describe it. And then the interesting thing with carbamazepine dihydrate is that like we can see very clearly, like where like the water molecules are aligned, like on the crystals. So and also like this the region where the water molecules align is also like the area where like it's actually also a cleavage plane of the crystal. So the crystal like material tend to like break along like this water molecule channel. So here just to show you the example like how like the width of the carbamazepine dihydrate like changes as a result of like dispersion using G3 morphology. You can see that as we increase the dispersion pressure, like initially we get a rapid reduce of the width of the crystal, and then after a while, then it started to reach like almost like a plateau. Even though you increase the dispersion pressure a lot, but then they don't break as much as compared to like the initial stage. And similarly, like we see the same like for particle length, they actually reduce rapidly initially. So using Gadri and Zhang's model, we can then apply like this method, this model, to then describe the breakage of acicular crystal. So here we did some like tiny changing of the model by then incorporating so instead of using like one single slit, narrow slit class of crystal, we actually use basically the full distributions of the particles and then do the impact test. So as a result of this, we need to give the weightage like to different like particle slit sizes and then fit them into this model here. And having done that, we can then come to this like a very nice correlation here. You can see that here we have beta L-glutamic acids. So we can you can see that they're nicely lined. Basically, we have this linear correlation, and then compared to benzodiazepines. So you can see that here the slope of this line represents like how breakable material is. So like here benzodiazepine actually has a lower breakability index as compared to the beta L-glutamic acids. So comparison of all the techniques that I've discussed today. So we have single particle tester. So the size analysis technique is by gravimetric. For Sirocco and RLS, they are by laser diffractions. Morphology G3 is by light microscopy. And the amount of sample needed for them, they vary differently. For a single particle metasterol, typically we require a few grams of the sample, and the same can be said for Sirocco RLS. But morphology for morphology G3, we actually have less. We can actually use milligrams of samples, and then we can perform, the breakage analysis of material. And impact velocity, we can measure it, but then for the other three methods, we actually estimate it using CFD. And velocity range for single particle tester, we can go up to a very high impact velocity. The same goes to Sirocco, but for RLS, it's slightly lower. But for morphology 3, because of the gap, the limitations of the gap between the dispersion spool, we can't actually accelerate the particles to a very high impact velocity. So the suitability for acyclic crystals, only morphology 3 is suitable for acyclic crystal. Both single particle tester, Sirocco, RLS, they are not so good in analyzing acyclic crystal breakage. The time needed for the analysis for Sirocco and RLS, they are very quick. You can do them, maybe within an hour, you get all the data that you need. But for single particle tester and also morphology G3, then you require a longer time period. Okay, so the next I want to move on to then say bulk tests. So here are just some examples of different bulk tests available. Then how we can characterize the breakage particles. And the very first one is an example of bulk compressions. So here you can see we can apply novel force, and then by putting a sample in the piston, we can then break the particle as a result of increasing the load. So we can do that by using a commercial device, say Instron mechanical tester. And then here's just an example showing you, how the particle break as a result of different pressures applied. And then if you're looking at then, how particle break as a result of shearing, then here we have, the shear cell of Bridgewater. And then essentially how it works is that you put some power in this annular shear cell here, you apply a normal load, you shear it, and then the particle break as a result of the shear deformation. And then here is an example showing you the mass of broken particle as a function of shear strength under different normal load. And then this is just correlations how we can describe the breakage of shear shear deformations. So here is just the equation here, and I won't go through them in details here. And here Neal and Bridgewater normalizations of the shear cell data. Again, if you apply this equation here, we can then nicely. If you apply this equation here, you can essentially unify this data into a straight line like this, which gives us a measure of the breakup, how the particle bridge, which so in other words, they give us some sort of predictive capability on how the particle will break under shear deformation. So here, just another device to show you how we can look at the attritions of materials under coupled effect of impact and shearing. So this is a device that we developed many years ago. What we call it a side tester. Basically, it's a short form for particle shear and impact tester. So essentially, this is a device developed as a result of collaborations between University of Leeds, Enzyme Dust Consortium, and also called Micron. So they built this device in which particles get impacted on this impact band, and then they get recirculated down in this roller box here, where here you can see where the particle gets sheared as a result. So basically, particle experience impact, and then as well at the same time shear. So using this device, you can basically look at we can use this to assess the performance of enzyme using this device here. So concluding remark for the talk. So micromechanisms of particle breakage depends on the failure mode. And for damage analysis under precise static deformation, nano-indentation can be used to obtain the hardness, the Young modulus, and the fracture toughness of material. For impact damage, the above properties can be inferred as lung parameters, as I mentioned earlier in Gary and Young's model, and we can also use commercially available devices such as Sirocco, RLS to assess impact damage. And we can also use light microscopy-based particle size analyzer like G3, to characterize the impact crystal. And the new technique is capable of characterizing the breakage behavior of acicular crystals and analysis of bulk breakage. Well, they require a model of mechanics of the particle assembly. And there may be a couple impact and shearing effects which should be borne in mind. So when if you have a process which they undergo, like different types of stressing, like most, then be careful, because like what you get might be very different from what you expected. And thank you very much for listening. And it's now time for a post-lecture assessment.